Kathleen Church, a postdoctoral fellow in the Semeniuk lab at GLEAR, the Great Lakes Institute for Environmental Research. Today, I'll be talking about how we can use agent-based models to predict population-level effects of microplastics ingestion in salmonids. Before I begin, I'd like to acknowledge that GLEAR is located on the unceded traditional territory of the Three Fires Confederacy of First Nations. As most of us already know, plastic pollution is a major global concern, as huge amounts of plastic pollution are already present in the environment, and more is continually added every year. This picture here shows a worldwide map of marine litter. Litter is represented by the yellow dots, and the majority of it, over 70%, consists of plastic waste. As this map illustrates, there's a lot of plastic waste present in the world's oceans. Plastic is especially harmful because it is not able to biodegrade but can only become smaller, and there are different ecological risks and impacts for different sizes of plastic waste. While larger plastics can harm animals through entanglement, smaller particles, like microplastics, can harm animals when they are ingested. Microplastics, by definition, are plastic particles between 1 and 5 millimeters and are frequently ingested by a wide range of taxa. A recent meta-analysis on the impacts of microplastics ingestion on growth, reproduction, and survival found that there was little consistency in these effects across taxa. Many impacts were neutral, which suggests that the effects of microplastics may be more subtle than anticipated, such as with more subtle behavioral changes occurring, rather than drastic physiological changes. Overall, the most common effect of microplastics ingestion across taxa was found to be a reduced intake of natural food items. Due to their small size, microplastics are not just restricted to the digestive system, but can be transported by the circulatory system and end up elsewhere in the body. Microplastics have been found to accumulate in different types of tissue and may build up inside the bodies of many prey species and then be transferred to predators once they are consumed. Although microplastics are able to transfer up to higher trophic levels, this has mainly been explored in laboratory studies, so we don't really know to what extent it does or does not occur in nature. Although plastic pollution and the effects of microplastics have been studied fairly extensively in marine habitats, research on the freshwater impacts of microplastics has only begun more recently. Microplastics are already present in virtually all freshwater lakes, rivers, and ponds, and these freshwater habitats grow more vulnerable to microplastic pollution with every year, especially in urban areas. It is already well established that freshwater fishes regularly consume microplastics, either by mistaking them for their usual food or by consuming them inadvertently alongside their target prey. Although physiological and behavioral impacts of microplastics ingestion have been studied for various species of fish, at this time it is still unknown how these effects will scale up to affect populations. For this research project, we are interested in the behavioral consequences of microplastics ingestion. Behavior can be very flexible, and it is this flexibility that enables it to be the first line of defense against human-induced rapid environmental changes, such as microplastics pollution. The effects of behavioral change can often be seen immediately, in contrast to having to wait, often for many generations, to observe the effects of natural selection. Previous research has shown that microplastics consumption can dramatically alter the behavior of different species of fish. Perch, as seen on the left, were less active and less able to respond to olfactory threat cues following microplastics ingestion. On the right is a common goby, which suffered a diminished ability to forage on live prey after ingesting microplastics. After consuming microplastics, zebrafish, as shown on the left, showed hyperactive swimming, while the European sea bass, as shown on the right, exhibited erratic and lethargic swimming, lowered velocity, and decreased resistance, or the ability to maintain its body position against a water current. Resistance is particularly relevant for salmonids, as they forage facing against the current. For salmonids, we know that freshwater species do consume microplastics, as microplastics have been found within the bodies of brown trout in a recent study. However, the behavioral and physiological effects of microplastics are still largely unknown for salmonids. For this research project, we are interested in determining how microplastics ingestion and interactions between microplastics and different stressors are likely to scale up to affect salmonid populations. We are also interested in determining how these impacts are mediated by the individual characteristics of the fish, such as their age, sex, and personality traits, as these characteristics may affect their susceptibility to or their consumption of microplastic particles. We are using behavioral models to address our research questions due to their many advantages relative to real-world experiments when tackling conservation concerns. Models are beneficial as they do not face the same logistical restrictions and time lags that are present in real-world studies that involve live animals. By using models, we can explore multiple future scenarios with varying conditions in a timely manner. We are using agent-based models, or ABMs, which model interactions between individuals and between individuals and their environment. Systems dynamics then emerge from these interactions. Agent-based models are multi-level models that can explore several levels at the same time, such as looking at both individual behavior and its effects on population dynamics. InStream 7 is a model from a family of ABMs that have been specifically developed for stream salmonid populations with 22 years of development and testing. This model simulates realistic salmonid behaviors with emergent effects on population, abundance, and persistence. We will expand this model to add varying concentrations of microplastics to the environment, as well as add the behavioral consequences of microplastics ingestion. We are using this expanded model to identify the different characteristics of the environment and the fish that result in populations that are the most and least resistant to the effects of microplastics after a 20-year period. For the environment, we'll be looking at the particle concentration of microplastics, temperature, and the presence of other stressors, such as habitat destruction. For the fish, we'll be looking at their age or life stage, the sex, as well as the personality traits. The health and stability of the population will then be inferred by the population size after 20 years and the demographic effects, as well as personality trait diversity present within the population. Microplastics represent an additional stressor for salmonid populations that are already struggling against the cumulative and possibly synergistic impacts of habitat loss, climate change, and disease. It is important to assess and mitigate the potential impacts of microplastics pollution, as this additional stressor has the potential to further devastate already vulnerable populations of salmonids. Thank you very much for listening to my talk, and please feel free to email me if you have any questions or comments on what I've presented. You can reach me at kathleen.church@mail.mcgill.ca, or you can message or follow me on Twitter at drkathchurchy. Thank you.